Hi everyone, welcome back to Causality with Boris, broadcast from Sobolev Spaces. In this video I talk about nodes, arrows and the chains of dependency. I talk about dependency graphs. The real gem will be in chapter 4. I will introduce Pearl's taxonomy. It describes 5 types of factors in a dependency graph. But I start with a question: what factors should be included in regression model? The average treatment effect is the difference between expected outcomes with and without treatment. We average them over the entire study population. We derive expected outcomes from a previously fitted regression model. You see, regressions relate outcome to treatment choice, pre-treatment conditions, and other factors that may affect outcomes. We enter unit-specific values of covariates into the model equation, find unit-specific outcomes, and then average them over the distribution of covariates. In observational studies, the averaging is done over the entire study population, that is, all treatment groups combined. In trials, the averaging is done in each group separately. However, we assume that each treatment group represents the target population. In both cases, treatment effect is the average of the individual effects, and it's averaged over the factors that might influence treatment choice and outcome. Here is the formula. We find the expected outcome for each patient based on the previously fitted model. Its regression coefficients are applied to treatment X and covariates Z, recorded for each patient, applied twice, so that we can obtain the outcomes for the studied and control treatment. Again, for each treatment alternative, we calculate the mean outcome for combinations of Z values. We add up the products of the mean outcomes and the probabilities of Z, and we do this twice, with and without treatment variable. So, treatment variable and covariates determine the expected outcome. But we haven't discussed the covariates yet. What should be included in regression model? The usual practice is to enter all available variables. Here is a better idea. How about only variables that affect treatment and outcome? Events make up reality. Something is always happening. Events occur, things change in response. One event follows another event. We begin with a network of dependencies between events. Graphs consist of nodes and arrows. The dependency graph shows events and dependencies between them. It also shows their direction. A simple but rich idea is the relationship of kinship between the nodes. Node A is the parent of B, and B is a child of A when there is a single-headed arrow from A to B. We use kinship language to describe chains of dependencies. For example, in environmental health, we look at emissions. Emission affects concentration, which affects exposure, which in turn affects dose, and finally health status. Other factors may influence the elements of this chain. Health effects can be influenced by health and age at exposure. Exposure depends on where you live, which in turn depends on socioeconomic status. These factors can be part of their own chains too. At the next level, we find dependencies between factors from different chains. For example, socioeconomic status can influence health. Those can depend on age. This leads to multiple and branching chains. Dependency graphs summarize what is known about factors affecting treatment choices and the occurrence of outcomes, directly or indirectly. In our running example, we look at the timing of surgery and postoperative mortality. Mortality here is compared between timing groups. Previous studies control for hospital and patient characteristics, but the relationship between the structure and processes of surgical care is not taken into account. Why this omission? Perhaps because of a limited understanding of the network of dependencies between all factors at work. Factors that influence both preoperative time and postoperative death, through direct influence or through intervening factors. Not until 2017, when Dr. Katie Sheehan, My postdoc at that time reads everything about worsening mortality after delayed hip fracture surgery and assembles a dependency graph with all factors involved. Impressive, right? Structure and processes of care and patient case mix, all here. This is the true power of the dependency graph. It integrates knowledge about how the world works, but it also gives us a meaningful basis for discussing knowledge gaps. A single graph can be used to frame an entire study field. Nodes and arrows are the basic elements of any graph. The main purpose of graphs? To show dependencies between the nodes. Nodes represent factors, whether they are observable or not, measurable or not. And sometimes nodes can represent concepts. We then relay them to available data. But always there are two designated nodes. One is for the treatment variable and the other is for the outcome. Arrows show dependencies between nodes and their directions. The origin node causes changes in the terminus node, and the value of the terminus node depends on the value of the origin node. It's often assumed that arrows represent direct influence. Of course, this is determined by the level of abstraction. You see, abstraction hides details. It emphasizes one aspect of reality at the expense of ignoring others. This is why arrows represent direct influence without a reference to the causation mechanism. For a given level of abstraction, an arrow pointing from one node to another simply indicates direct influence. The basic method of health research is to quantify differences between treatment groups. Our premise? Well, there is a mechanism that brings about the difference. But uncovering that mechanism, explain how it exerts the difference, is another level of abstraction. Here, we aim to find out how much outcome depends on treatment. We want to prove that intervening in X changes Y. This is why one arrow always goes from treatment to outcome. It represents a putative relationship we want to test, a relationship that is the subject of causal analysis. So, all arrows imply direct influence, right? Here's the thing. The missing arrows represent assumptions about the absence of direct influence. Just make a mental note here for now. We'll come back to this idea later, when we talk about dependency graphs in more detail. Let's take a step back and think of our goal here. We need to make treatment groups comparable. And our first move is to understand what makes them different. We review the literature and assemble a dependency graph. It's a summary of what is known about factors that explain variation in treatment choice and outcome occurrence. Now it's time to sort these factors into groups, and UCLA professor Judea Pearl does it for us. Here is his taxonomy. Some factors affect outcomes, some affect treatment, and some affect both treatment and outcome. Notice that these three groups consist of pre-treatment factors. They get their values before the treatment is applied. Yet some post-treatment factors can mediate the effect of treatment on outcome, and some depend on both treatment and outcome. Brilliant, isn't it? We can use Pearl's taxonomy for classifying factors and their dependencies. There are no intervening factors in this taxonomy though. Factors that influence treatment and outcomes through a chain of dependencies. This extends the notion of approximate common cause, acting through the direct influence. Factors in this group are distant common causes. Let's look at this dependency graph. It shows the phenomenology of timing and mortality after hip fracture. It shows all known factors and their relationships. Solid arrows show the directions of dependencies between the nodes. The dotted arrow represents presumed effect of timing of surgery. We color code the nodes according to Pearl's extended taxonomy. Green nodes represent factors affecting timing of surgery. Blue nodes affect the onset of death, and orange nodes influence both the timing of surgery and its outcome. Their influence can be direct or indirect. The orange arrows show the dependency chains for indirect influences. Let's look at this graph again. One arrow shows the preoperative time directly affects postoperative mortality. Not surgical complications here, they mediate the effect of timing on mortality. In my next video, I use this taxonomy to explore causal diagrams. So let's summarize. We start with the question, what should be included in a regression model? Our guiding principle is only factors that explain variation in treatment and outcome. We gather existing knowledge about dependency between them. Using nodes and arrows, we construct a dependency graph. Pearl's taxonomy sorts factors from a typical graph. Some of them affect treatment, some affect outcome, and some affect both treatment and outcome. Some post-treatment factors mediate the effect of treatment, and some of them depend on treatment and outcome. You watched another episode of Causality with Boris. Keep on watching.